According to legend, Isaac Newton was one day sitting under an apple tree when an apple dropped on his head, and he began wondering why. Why does the apple always fall to the ground? Why doesn't it fall to another tree or to the moon? Speaking of the moon, why doesn't it fly off into space? What is it that keeps it in motion around the Earth? So Newton proposed a pretty radical idea for his time. He put forth that what caused apples to fall out of a tree was the same force that kept the moon in orbit around the Earth. This universal law of gravitation was found to be able to describe the movement of almost every body in the solar system. It was also able to describe the forces acting between an apple and the Earth. One of the orbits that Newton's universal gravitation could not accurately predict was that of the planet Mercury. Now, planet orbits are not perfectly circular. They are more of an ellipse. This means that there is a point in space where the planet is closer to the Sun during its orbit. This is called the perihelion. For most planets, the perihelion is pretty consistent. But Mercury's orbit around the Sun shifts slightly so that its perihelion bumps forward just a bit. Even after accounting for the gravitational effects of all the other planets, Newton's universal gravitation could not accurately predict Mercury's orbit. Actually, for quite a long time, it was believed that another planet, Vulcan, was nearby, yet to be discovered. So Newton had now presented two ways to describe mass. The first was describing mass in terms of a gravitational field. An object with a mass is affected by the gravitational field of whatever body it is on, and we call this the gravitational mass. There is also the idea of inertia, and that is a certain amount of force required to change the motion of an object, which we refer to as the inertial mass. So Newton had these two theories to describe the same phenomena. A couple hundred years later, Einstein came along. He never really liked the idea of two theories to explain mass, and he really didn't like that Newton's theory relied on some unseen, mysterious force called gravity. He wanted a way to unify both theories into one. So he sat down, and 10 years later, he had developed his general theory of relativity. General relativity explains how space and time work around massive objects. Einstein comes up with the idea of the space-time fabric. When a massive object like a planet or star appears, the fabric is warped in towards the mass. The easiest way to visualize this is like a trampoline. When nothing is on it, the fabric is all nice and flat. But take something big like a bowling ball and place it in the middle. The fabric of the trampoline will curve around the bowling ball. If you were to take a marble and send it along the fabric, the marble would follow the curved path and begin to orbit the bowling ball. So kind of like a ball rolling down a hill, this curvature of space-time causes an object to accelerate. We call this effect gravity. Now imagine that in 3 dimensions. A mass causes the entire area of space around it to curve in towards it. Since objects like the path of least resistance, they are going to follow the curve of the space-time and move around the more massive object. That is what you feel as gravity. Now, now imagine in 4 dimensions. Imagine the curving of time along with that. That one's a little tougher. Throw a rock into a pool of still water. What will you see? From the point where the rock hits the water, a series of ripples will move out in all directions. Now imagine 2 enormous bodies colliding in space. If we accept the idea of space-time, that collision will disrupt the space-time around it in a way similar to the rock in the water. These ripples in the fabric of space-time are called gravitational waves. Einstein's general relativity predicted the strength and frequency of these waves. So all that was left was to figure out how to detect them. In theory, the gravitational waves produced by a violent collision as 2 black holes interacting, when they pass through a detector, will alter space by no more than 10 to the negative 19th power. Okay, so how big is that? Well, a centimeter is 10 to the negative second. A human hair has a width of around 10 to the negative fourth. A micrometer is a millionth of a meter, and that is about the size of an average cell. When we are talking about atoms, we get into nanometers, or billionths of a meter. If we keep going on another 10 magnitudes, then we get to the precision needed to detect a gravitational wave. So what kind of an instrument can measure to that precision? Enter LIGO. LIGO is the Laser Interferometer Gravitational Wave Observatory. It consists of 2 laser interferometers located thousands of kilometers apart, one in Livingston, Louisiana, and one in Hanford, Washington. Okay, so what is a laser interferometer? Well, it all starts with a laser. A laser beam passes through a beam splitter, which, as you might guess, splits a single beam into 2 identical beams. One of the beams continues on the original path while the other is deflected at a 90-degree angle. At the end of each arm is a mirror. This mirror reflects the beam back to the beam splitter where the two beams merge back together. The resulting beam travels to a detector that measures the brightness of the merged beam. If the brightness of the merged beam is exactly the same as the original beam, then nothing has happened. If a merged beam is brighter or dimmer than the original beam, that means that the distance that one of the split beams traveled is different than the other. And since both tunnels are designed to be exactly the same length, that must mean that something has since changed the length of one of the tunnels. So here's a little bit better explanation of what an interferometer does.
To measure this stretching and squeezing, Ray turned to a device called an interferometer. A laser beam is split and sent down a pair of long perpendicular tubes, each precisely the same length. The two beams bounce off mirrors and recombine back at the base. The light waves come back lined up in such a way that they cancel each other out.
And you add them together, you get nothing. You get a zero, a big fat zero. No light gets detected at the photodetector.
But when a gravity wave comes along, it distorts space and changes the distance between the mirrors. One arm becomes a little longer, the other a little shorter. An instant later, they switch. This back and forth stretching and squeezing happens over and over until the wave has passed. As the distances change, so does the alignment between the peaks and valleys of the two returning light waves, and the light waves no longer cancel each other out when added together in the recombined beam. Now some light does reach the detector, with an intensity that varies as the distance between the mirrors varies. Measure that intensity, and you're measuring gravity waves.
The light takes longer time in here than it did in this arm. Now it takes a shorter time, and these things don't cancel so beautifully anymore.
Remember, the change in arm length caused by a gravitational wave can be as small as 1/1000th the width of a proton. So we are trying to measure with a precision of 10 to the negative 19th power. Think about Earth and the next nearest star from us, Alpha Centauri. This is a pretty big distance. Now imagine trying to measure the change in that distance that is the width of a human hair. In order to accomplish this precision, we need a really big instrument. In real life, a single LIGO laser interferometer is a kilometers-long instrument. At the Livingston and Hannaford observatories, the laser and monitoring station are housed in one large building. The laser used in the LIGO observatories are rated at 200 watts. Compare this to the commercial laser pointer you can buy at 0.005 watts. However, for LIGO to operate at full sensitivity, it needs a laser that puts out 750 kilowatts of power. A process called power recycling, where mirrors are placed in between the source laser and the beam splitter. Essentially what happens here is that the mirror reflects light coming back from the arm gets reflected back down the arm. This reflected beam adds to the new incoming beam. More photons equals more power, and the ending beam power increases. The laser and beam splitter are housed together and attached to two long perpendicular arms. The arms of LIGO are each 4 kilometers long. Each arm is actually one of the largest and purest sustained vacuums on Earth, where the pressure inside is 1/trillionth that of the air pressure at sea level. To accomplish this, jet engine-like pumps suck the majority of the air out of the tubes. The tubes are then heated to between 150 and 170 degrees Celsius for 30 days. This drives any residual gas molecules out of the space. Finally, ion pumps electrically charge any remaining particles and attract them away with an opposite charge. In all, it takes a total of 40 days to remove the 10,000 cubic meters of air in each of the arms. The length of the arm is important since the further the laser beam travels, the more sensitive the instrument becomes. Even the 4 kilometers is not really enough to get the precision needed here. So scientists added, you guessed it, more mirrors. The beams traveling down the arms are reflected 280 times before they are allowed to merge back together. At the end of the vacuum tube is a mirror, but not just any mirror. These are the smoothest mirrors ever produced. They are made of very pure fused silica glass and absorb just 1 in 3 million photons that hit them, which means that nearly all of the laser light that hits the mirror is reflected back. Not only does this prevent the mirrors from heating up and changing shape, but it also keeps that beam of light that has been traveling for 1,100 kilometers going along the right path. Of course, the sensitivity of the interferometer makes it susceptible to the smallest outside interference. LIGO's first line of defense is an active damping system. The internal seismic isolation is a series of devices that purposefully perform counter movements when it senses ground movements. As a result, the entire system remains perfectly level. Passive damping is really just a system of 4 pendulum masses that work to keep the mirror from moving in the first place. The mirror itself is suspended at the bottom of this pendulum system by a 0.4 millimeter thick fused silica glass fibers. Then, to top it all off, there are 2 observatories several thousand kilometers apart. The only way to definitely detect a gravitational wave is by operating in unison with a distant twin so that local vibrations are not mistaken for signals from gravitational waves. Because of its sensitivity, LIGO will pick up nearly any vibration in the Earth. Things like earthquakes, noise from the outside, even people driving in the parking lot can all be picked up and mistaken for a gravitational wave. Having 2 observatories a large distance apart allows scientists to filter out anything that is not actually a gravitational wave. So what exactly are we looking for? When 2 objects orbit each other, they radiate gravitational waves through space. If they are big enough and if we are listening, we can detect a nice even waveform. Now, if we can detect a wave, we are detecting energy, which means that the orbiting bodies are losing energy. As this happens, the orbital distance between the 2 bodies decreases and the speed of the orbit increases. We can see this happening in our recorded waveform as the frequency and amplitude increase. Eventually, the 2 bodies begin to merge together, forming a new single larger body. Eventually, the 2 bodies begin to merge together, forming a new single larger body. The 2 briefly, rapidly oscillate, creating an increase in the amplitude and frequency of the waveform, called a chirp. We can even scale the frequencies of the waveform into the audio range we can hear. This waveform was numerically predicted by the general theory of relativity as shown by the red line. The gray line shows a reconstruction of the LIGO-Hanford gravitational wave pattern, which is just simply amazing how much it matches the prediction. Now, it's one thing for one observatory to pick up a waveform that is believed to be formed by a gravitational wave. But the sensitivity of the observatories is so high that the tiniest vibrations can interfere with the signals. So when both observatories, 3,000 kilometers apart, detect the same waveform, those local vibrations can be filtered out, and scientists know that they must be seeing a gravitational wave affecting the Earth. LIGO has 2 sister facilities under construction in Germany and Japan, and is working with another observatory in Italy that has recently come online and is ready for collaboration. There's also plans for a 6th site in India.